Hi guys, today I'm here to talk with you about architecture. And architecture in the sense that you have already created a program that works today, but then in time something happens and your program isn't as successful as you wanted. So why could it be that a successful program becomes unsuccessful? One of the troubles could be the amount of users. So maybe your system works fine for now, but then there comes a bit more users and eventually a lot more users, and your software can't handle that. It could also be increased functionality, meaning that at the moment you have a small system and it works okay, and then there gets more and more functionality into your system, and eventually it's not okay. It could also be that today you have one user, then it becomes all users in the nation, and eventually all users in the world. Likewise, it could be one system, a new system, and a new system. Or it could be that your customer just wanted a little bit of software, a cheap one. It's not necessary to have, but it could be fun if your software could create some certain reports. And then you create this program, this software, and after a few years your system breaks down. All system breaks down eventually. And then they discover that it wasn't just nice to have, it has become necessary to have. So what they want from the new system is high availability. To attack all these problems, all these scaling problems, I found two sentences. One of them is single responsibility, which I have stolen from Solid. Solid is a way, a paradigm that we will look at later. And I have stolen low coupling from Grasp. We all know the 3 layers, which means we have a system and the user is happy. The system is actually 3 layers. It's something of a view, it's something that the user can interact with, the user interface. It's also some functionality hidden in a controller layer, for example, and a lot of data hidden in our data model. So the 3 layers could also be a VPF application, a desktop program, as we have done many times, or it could be a web page, an interactive web page with Ajax and Java and stuff like that. And on the server we could code it in C# or PHP, and the data layer could be NoSQL, MySQL, SQL, files, whatever that stores data. And this is actually not just 3 layers. We call it 3 tiers because these are 3 different servers, 3 different computers at least. So your client could be either a desktop program running on your client computer, or it could be a web page, an interactive web page running on the browser in your computer. Then we have a server that generates all the stuff for the browser, and we have a data layer that generates all the data, stores all the data for the server. We could also expand it. We could put in another box, call it security. It could be a firewall. It could be a program that routes all requests further onto the server if you are an authorized user. It could be that the server is not just a server that does everything. It could be presentation and business layers were separated into each server. Or it could be even that we have a server only for calculations. So this is just layers as we used to, but separated into several servers. So this is separation of concern in active play. This means that if one server doesn't have the power, we can scale it. Another way to scale it is service-oriented architecture. This is where we look at services. not as in layers, but still it's a separation of concern. So let's look at the system. This system contains lots of services. We have what we could call a main service, which could be the user interface, it could be the web page. And this service is gathering information from other services that might gather information from other services as well. It is not clearly defined where these services are located. We'll look at that in a few seconds. All we know is that a server does something. Maybe it calls another service, maybe it doesn't. Maybe it stores some data on its own database or file system, maybe it doesn't. It's just functionality in these boxes. As we see it here, there are some high coupling between, for example, service 5 and service 4 and 6, or service 1 is coupled to both 2, 3 and 7. Still, they're not as high coupled as if they were all written and running on the same program. But we can maybe do it a little bit better. So here we have introduced a queue and a bus service. The queue is just receiving requests and queue them up if it's not able to send them off as quick to the bus. So the queue is only to receive and pass on requests, and the bus is then responsible for selecting where the request will go to, which service. So it could be calculate price. So if the customer wants to get a price on an object that he might consider buying, he will request the queue for a price. And the bus is intelligent enough to know that the service 1 is the one that calculates the price, but maybe service 1 needs to know what kind of user you are. Are you an ordinary user or are you a gold user with extra discounts? So service 1 has to request the queue for more information. The bus then knows from your request from service 1 that it needs to ask service 2 to gather the information about the user. Let's look at service in practice, because we all know it, we have seen it lots of places. For example, here at Facebook, you can find information about a hotel, and you can click the map to see where the hotel are located. That doesn't mean that Facebook have an entire map of the entire world with everything in it. We know that Google has a map with everything in it, all hotels and buildings and pictures and stuff like that. So that's why when you want to know where a hotel that has a page, a group in Facebook, if you want to know where this hotel is located, Facebook is receiving data from Google Map and show you the Google Map instead. So this is Facebook retrieving data from another service. This is another example. Someone bought a lot of computer parts, and one of the parts, the memory parts, the 2 × 4 GB of memory, is ordered and is ordered at the remote storage. This means that this computer shop is able to contact the remote storage to see how many they have on stock. Another example here is from Endomondo. When you want to log in, you can either log in with your email and password, or you can hit the login with Facebook button. That means that Facebook must have a service that can validate the user in a way that Endomondo can use it. So in this case, services are business intelligence, business stuff that are put out for display for other companies to use. And Facebook has an API that you can access yourself. It is not only for Endomondo and other web pages. You could use it as well. So let's see, how do we scale stuff? If not with layers or with services. Cluster is one of the ways. If you have a system, we call it system 1. You can clone it so you have 3 systems, alike systems, totally equal to each other. And then you have what is called a load balancer. And of course, the 3 systems must talk with each other individually. This means that when the customer wants to connect to system 1, he does it through the load balancer. And the load balancer is 100% transparent. He won't notice that he goes through this load balancer. And what the load balancer does is that it redirects his call, his request to system 1 to any of the 3 system 1 servers, the one that has the least amount of work, the least busy one. So this is an easy way to get a system to be 2 or 3 or 4 or 5 systems. This could also be combined into, for example, the service bus, the service queue bus SOA architecture as here. So let's say that service 1 is a price calculator and service 2 is handling the user profile. And let's say that it takes that high amount of work to calculate what kind of user you are. So service 2 is overloaded. Then you can mirror service 2 into 2 servers and put in a load balancer in front of it. This way we have scaled service 2 so it has more power than service 1 and 3. But what about the databases then? If we have a cluster with 3 service 3s, server 1, system 1 was it, sorry. If we have 3 system 1 servers and they all use the same database, will that not just overload the database? So how do we deal with databases? One way could be to separate reads and writes. I know for a fact that Facebook does this. You don't write much to Facebook, but you read a lot from it. So separating them, so you have an entire database for writes, an entire database for reads, and then from time to time you run a synchronization job. We could also look at this in this way. So the blue database is the one you write to, and the red one is a fast one that you read from. So this means that you can format the red one with cluster indexes and stuff like that to optimize for requests. But we have a rule: whenever we use more databases than one, we have to consider these 3. Consistency. This means that all clients see the same data regardless of the situation. This is not consistency. We know for a fact that if you write to the blue one and there's a synchronization, the gray arrow, what if the synchronization job hasn't run yet when you request information from the red one? So they don't contain the same data all the time. If you go to Facebook and hit F5 and someone writes a new story there, then it will show up as a new story. And if you hit F5 and reload the page, sometimes it disappears again, meaning that we don't have consistency. If you go to the bank, you of course have consistency. It's not good enough to know that sometimes you have $1,000 on your account and sometimes you have only 800 because it has updated, and it's not always you see the same data. So in a bank, you of course always want to see the correct amount of data. Availability means that are the system responding whenever you want it to respond, and partition tolerance means do the system respond okay even if you have lost synchronization, even if you chop off one of the servers. So let's look at this case. We know that we don't have consistency. The red and the blue are not always alike with the same data in it. What about availability? Okay, if the blue one is dead, then the red one might still continue working. So we have higher availability. And partition tolerance. No, we don't have it. Oh, sorry, yes, of course we have it, because if you cut off the gray area, then the blue and the red will still respond in their own way, like they used to. And then eventually when you can synchronize the data again, yeah, then the red one will become up to speed. So we have availability and partition tolerance, but not consistency. The good part about separating reads and writes is, in the case of Facebook, for example, we have lots of reads and a few writes. Maybe only 1 billion writes and 100 billion reads per hour. And we can do that by mirroring the blue data to several red ones. They could be located all over the world, so you have a red one in Asia and a red one in the US and a red one in Europe and stuff like that. But what if you have like 1 million red databases? Then your blue database will be totally overloaded with just mirroring data, and it won't have time to receive the right data. So whenever people want to write a new story in Facebook, they can't, because the blue one is so busy updating the red ones. That's not a good idea. So to prevent that from happening, we have this yellow database. Now the blue mirrors its data once in a while to the yellow one, and it's the yellow one that mirrors its data to all the red ones. And now the blue don't have to use that much time on mirroring its own data. And how about consistency here? No, don't have consistency either. We can't guarantee that the blue, the yellow, and especially the red ones has exactly the same data all the time. But availability is high. If we lose a red one, yeah, okay, doesn't matter. You can then just connect to any other red one. What if you lose synchronization? Yeah, the red ones don't care. They just don't have up-to-date data. There are situations where you have lots of different systems. If you take a supermarket, for example, it could have customer data in one of the blue ones. It could have its entire system, just handling customer information. It probably have an entire system handling prices on all the items in the supermarket. And it might have an entire system handling orders or employee data. But what if I wanted to generate a report about how much Ms. Larsen has sold this year? Ms. Larsen's information would be in one of the blue ones because she's an employee, so we have the employee data in one of the blue ones. But every time she sits and checks in customers' stuff, selling them, receiving money, talking with the customers, it is on another system. And if she places order on one of the supermarket's own customers, it will be in yet another blue database. What if we want to make a report with all these data on all the different blue ones? Yeah, that's the principle of a data warehouse. So we format all the data to be as much alike as they can be and store them all in one database. So now all our report data will be in the red one. Does that affect our consistency? Yes, of course it does. It's not the same data we have in the blue and the red ones. It's not even the same data we have in the blue ones. But they will be what we can call eventually consistent, but not consistent. Availability is high, yeah. And partitioning tolerance, yeah. If you if you cut out the gray areas that synchronize and maybe modify and synchronize our data, the red one will still have data, just a bit older data. Then we have this active failover. That means that whatever you write on the blue one will be written on the red one instantly, and vice versa. So these will always have the same data. Always, you say, but we have some synchronization. It takes time. So what if I write stuff to the blue one and in the next clock cycle request the same data from the red one? How do I achieve that it will be the newest and always the correct data then? Waiting. It is as simple as that. The SQL server have algorithms that enables these synchronizations to run whenever it has updated data on one of them. It mirrors them to the other database. I don't know how, I don't care, I just know that it can do it. And if it is synchronizing just as I requested, it will let me wait until it has the right data for me. So here we have high availability, because if one of the databases die, we can continue working on the other one. What about consistency? That's high here as well. These are totally mirrored. It's a failover. If one of them dies, the other one has all its data. But partition tolerance. What happens if we cut the synchronization job, for example, and the two databases can't talk with each other? Usually they will go into read mode, read-only mode. So you can't write to any of the data, and thereby it has still consistency, because you can't modify the data. You can also have this load balancing high availability. That is actually the same, just spread over more than two databases. So how do we make all these synchronization jobs? We use a technique called extract transform load. It's not something that we'll teach you. This is purely information about how it works. ETL is used for example, data warehousing, where we read data from lots of different systems and format them so the data will become most alike, as much as like as possible, and then we store them in a data warehouse. An ETL job is usually some graphical tool, where we can see here in 1 and 2 is two different databases where we extract some data in 1 and 2 and join them in this free SQL join. Then we do some more with it, and in this case print out a report. So this is a standard ETL job. So we could also talk about scaling our hardware. In this case we have a server with a CPU and some memory, and it's easy to, in some cases we can buy more CPUs and more memory, and thereby scaling the system out, meaning that we upgrade the server. But it's not always something we could do. Some server can only contain one CPU, or you have already bought all the CPUs that you can put in your server, or you have even bought the biggest, baddest server in the world. So if you can't scale out, then the only thing you can do is scale up. Scale up means buying more servers. And buying more servers means that you have to have the correct architecture. Otherwise, your scale up will fail. I have still one bit of thing more to tell you here. We could use a system called RAID. It is because most failures on servers is on their hard drives. So how do we protect data on an unstable device like a hard drive? One possibility is using RAID. I won't go much into the details about RAID. You can read about them on the internet. RAID 0, 1, 5 and 10 is the most used. There are probably also a 2, 3 and 4 and stuff like that, but I don't know about them. In order to run your disk in RAID, you need a RAID controller. You can also use software RAID. It is built into both Windows and Linux and stuff, and other operating systems, iOS as well. But this is software, and if you need it done correctly and in a way you can trust it, it has to be a RAID controller. And these are usually not cheap. RAID 1 means that you have 2 disks with exactly the same data on it, while RAID 0 is that you write first on one disk and then on the other one. RAID 1 gives you high security and RAID 0 gives you high speed. And of course you can combine them, but that takes 4 disks. Then there's also the thing about the disk plates. We have here an ordinary home server, home computer disk. This is maybe a 4 terabyte disk or 6 terabyte disk, and it has lots of plates. And each plate has one read-write head. And a read-write head can be in only one position. What if you are 1,000 users accessing 1,000 files at the same time? That's not good for a disk like that, because the read head can only be at one location at a time, servicing one user with one file at a time. And that's plenty for a home computer, but not for a server. And that's why you in servers usually use disk with only one plate, but then you use a lot of disks. And if you have a really expensive professional server system, then you have pieces of software to handle where the files are located. So if you know, or if the system knows, that 2 files are usually used at the same time, then it will store these 2 files on different disks. So 2 different users are able to use these 2 files because they are on each own disk. Back to scaling. In theory, we really want to be able to get 10 times the power if we buy 10 servers. But if you're using some of the patterns like the cluster solution where all the free servers in my graphic talk with each other, if you're using a high availability consistency database, then you'll use lots of time mirroring the data every time someone changes them, and that costs time. So then we won't have the blue line, and then we won't have 10 times the power with 10 servers. This is important if you want to scale your software, have high scalability. You have to think it into your architecture. Think of Facebook, that maybe have 1 billion users at the same time. So they have sole consistency, as that is one of the most expensive patterns. And without consistency, or eventually consistency, we have high availability, we have partition tolerance, and we have a highly scalable solution. So what is in this box that I have called a system? Usually we have done it in DLL files, but DLL files is not as good to scale because they are referenced from other parts of the program on the same server. So usually we think of a system as a server, or at least a virtual server with lots of virtual machines on it. This is also highly scalable. And the errors, in our old programs, they were references between methods or DLL files. In this system, it could be a file stored on a file server, but usually it would be sockets, web API, SOAP, RESTful services, stuff that talks over the network. And it could also be over virtual switches in a virtual machine environment. So now we've talked about what good architecture are. Think of this triangle. So we know that we have something about money, time and quality. And that means if you make a really high scalable architecture, it will take time to plan and to draw these architectural things to come up with a good analysis of and a design of how to make a high scalable architecture. and it costs time and money. And it's not always a good idea to go for the best, most scalable architecture. It depends on the situation. Why do an architecture that can scale to 1 billion users if you only expect 1,000 users, for example? So it's about cost and benefit. So if you make a solution that is not scalable at all, it will cost a lot of money and time to scale it at a later date. If you think of the system as a highly scalable system and you won't need it, you have used lots of energy on making it highly scalable. And it costs money that you could have saved. So finding the right balance is also important. Of course, there's a lot more to it than what I have talked about in this little video. So here are some links that you can read up on. Especially I like to recommend the free SOA links, especially the 10 examples of SOA in use in 2010 and the secrets of Amazon's success. They both tell how to use, both tell how companies has used SOA. It's not enough for me to talk about it. You have to do some work, some exercises to gain some experience in working with this. And the first is to create a bank. I would like to draw your attention on the requirements here. So create a new customer, change customer information. There are some customer things. So remember that if you, for example, make SOA solution, a service-oriented architecture, then there are some customer stuff here, there are some transaction stuff, there are some loans and some reporting stuff. And remember that a service could have its own database, so it's not enough to say that I like this database architecture, this database design pattern. It depends on what you want to accomplish. Is it the same database architecture in all the cases? How many SOA boxes do you want to create here? Or are you going for the layered approach? Or just clustering? It would be easy to stuff it all in the same server and just cluster it to 3 or 4 servers. But remember, clustering is not scalable to 10 servers or 100 servers. Not efficient. The next exercise here is about creating a search machine. Think of Google. It has some web crawlers searching the internet for changed or new web pages, so it writes its information on new or changed web pages to a server, to a database. And then there's all the users like you and I that use Google from time to time. So does the read-write ratio of the database influence the way you will organize your data? Does it influence how you build the rest of the architecture, layered services or stuff like that? So what's important here? How scalable do you want your solution? Then we have this little hobby webshop. So we don't want to make a webshop that can't scale at all, but we still want to make it cheap. So again, what is read-write ratio? How will we create the database in order for it to scale at least a little bit? We are on target here is nationwide, so we don't need to have that high scalable solution. This one, on the other hand, is a weather helper, collecting weather information from private gardens every 10 seconds. So we will have a lot of writes here. And then we'll have this report generation stuff, where it will have some lowest temperature, for example, lowest and highest and average temperature in hourly reports. So we'll have a lot more writes than reads. So how do we accomplish this with a good architecture? And then back to the web shop. what if this guy who created this web shop comes up with a really good idea and he wants to make a more general web shop that everyone can use? You can buy his code and then you can create your own shop. Will that affect the architecture, the overall architecture of his system? So through these exercises, you really need to look through the PowerPoint and all the links. And as usual, you're more than welcome to send me your solution so I can give you feedback. So until we see each other next time, thank you for watching. I'm looking forward to seeing your exercise answers.